Okay, awesome. Yeah, thanks for coming, everyone. It's my pleasure to introduce Bert Chan. Bert Chan did his bachelor's in computer science in Hong Kong, right? And then a master's at Lund University. Oh, you're already going to introduce yourself, but he was working now in a branch of Google, and he'll tell you a little bit more about this as a research software engineer. So he's doing research within Google's ecosystem. And how I met him originally was where else? Through Twitter. And he's posted some really cool animations of his mathematical framework called Lenia. And that's when I was intrigued. So I looked it up, and his framework was open source, posted on GitHub, and it has 3,000 stars, I think, on GitHub. And so it's a really popular framework used in a lot of different areas. And I think it has obvious parallels to cancer, but hasn't yet been applied to cancer, right? I guess maybe coming soon, so stay tuned. So thanks for coming to Moffitt, and we're excited to hear more from you.
Thanks, Jeff. I just wanted to say that those of you that made it here today actually going to get lunch on me. So I'm taking everyone to lunch. So they didn't make it, but the rest of you did. We'll go for lunch now. Please take it later.
Okay, so thanks for introducing me. So as you said, I'm now working in Google DeepMind, which is, I was in the brain team, but now at the merger, so now I'm under DeepMind. And I'm now working in Google, in Tokyo. So you can see this photo is Sakura season recently, so they have very beautiful flowers. And I'm researching on topics like artificial life, complex systems, or using evolutionary computation as a method. So the major topic I'm going to talk about is Lenia, which is some kind of abstract dynamical complex system. And you can use for different, depends on how you extend the system. You can use it to simulate different physics-like dynamics or even biology-like phenomena. And in the biology case, we can call this system some kind of artificial life system. And the patterns we can find in this system are emergence and self-organizing. And they're also robust against noise from the environment. In these projects, I usually use evolutionary algorithms or even use machine learning or deep learning methods in this system. That means I'm using AI. And on the other hand, I will, in these studies, I will try to build things from the bottom up, like agency, connection, or even collective intelligence, so that I may try to use Lenia to do something back, contribute back to the study of AI. And also as an artificial life system, we'll try to use it to understand life itself. Like, how can we define life? What will be the origin of life? Questions like that. So I would like to talk a bit about agency and connection. So agency is some kind of, you have an individual cell, and you have the cell or the entity have a kind of perception from the environment, and it can do some actions to the environment. And also the agents have certain kind of goal directedness. So a cell or a multicellular organism will be some kind of agents. And also like robots or like a software agent is also some kind of agent. There are some very interesting kind of agents. We call it collective agents, like those green algae, or forming a sphere, or like ants forming a bridge, or even human beings forming a team. They seems like they act like agents, but it's a question that are they actually, can we actually describe them as an agent or a new form of entity? So also in connection, we have two views of how can we discuss agent connection and agency. One is the mechanistic view, which is very common in the AI or machine learning world. That is, we just treat them as a presumed agency, that like a robot. So everything is fixed. We have fixed sensors, we fixed legs or arms. But there's also another kind of inactivist kind of view. It's usually biology, life forms will have this kind of connection. That means the agent itself is not well defined. You have a bunch of cells, like millions of cells, but the borders between their entity and the environment is not always well defined. Like you can imagine a cell, cancer tumor. You can say it's some kind of entity, but they keep changing its shape, keep changing the boundary between the tumor and the environment. So in this view, that the agency is somehow Bert, and the agency is self-maintaining dynamically through time. So I like one saying in biology is, or in artificial life or artificial intelligence is, why some entity exists. So one saying is, I persist, therefore I am. That means some identity, like a tumor, it has to retain its individuality through time, or else it will just disappear. Or even a life form, multicellular life form, like this cell, even a unicellular cell life, if it's lost its self-organization power in some time, it will just cease to exist. So I will talk about self-organizing systems. Yeah, I should insert a slide before talking about a bit about artificial life. So I will just speak. Artificial life is a research field. There are three streams of or main topics in artificial life. So one topic is synthetic biology. That means they play with those rules in biology, like how can we, for example, in DNA we have ATCG, but some researchers, they will like invent some other letters in the DNA letters. And also they will play with some, how can we produce some protocells out of biochemical substances. So that is like synthetic biology, the roots in artificial life. Another one is making some robots or machines, like a bird-like machines or humanoid robots. That is one stream. And the third stream is we call computer simulation. That is the software side of artificial life. That is what I'm working on. So in this computer simulation, like this slide is showing, we play with many different kind of simulations, like particle systems, swarm chemistry, or in the middle you can see some particle system. They come up with this kind of very interesting self-organizing patterns out of very simple kind of rules. And also from reaction diffusion system, you can see this like a moving dots, which is kind of interesting. So this kind of complex system what we mean by complex system is we have many components like cells or particles. And we also have some local interactions, like, which each components only see at the immediate neighborhood. And by applying these rules, we will see these patterns emerge or self-organize into existence. Like we have to see new forms of entity. And one thing is the whole is not only more than the sum of components, but actually different from the sum of components. One brand of self-organizing system or complex system, which I'm working on, is a cellular automata. The most famous one is from John Conway, who invented this Conway scheme of life, which the system is one of the most simplest form of complex system. You have a checkerboard of grid. Each cell of the grid is either 0 or 1. 0 means dead, 1 means alive. And you have this kind of if then else kind of very simple rule. And each cell is seeing the immediate X other cells. So it's kind of the simplest form you can think of, this complex system. And you can find these emergent patterns like a glider moving along the grid. And also this is called a glider gun mechanism. It keeps spitting out gliders. So the Conway scheme of life is like 50 years ago, but in the recent like 10 years, we see because of increasing compute power, you are starting to see this kind of continuous CA. So this kind of compute continuous CA is we start to play with these different kinds of rules. For example, if we have dead or alive, so how about just put the values using real numbers or floating point numbers, or about the neighborhood? How about not just the nearest more neighborhood that is X cells, but how about like a 10 by 10 cells, or even bigger, like 20 by 20? About the update rule, how about not just update discrete updates, but how about using fractional updates rules? Like we calculate the value, but only update 1/10 of the value back to the original grid. So all this kind of play with the rule, enlarging the horizon or the possibilities of the system. So we can see this kind of smooth patterns coming out from the system, which is very, very different from the discrete type of kind of CAs. So Lenia is actually one kind of such kind of continuous cell automata. You can see in these animations that the 2D world and also in the 3D world, we see this kind of very different kind of patterns. Also, the dynamics, we can describe this dynamics as some kind of differential equation, like in the bottom. You have this differential dynamics, but you can also have the integral dynamic. The integral parts of the equation is the K convolved with A. This is something different from the usual differential equations. So the basic idea of Lenia is you now have a world which is just a 2D or 3D grid of values. And then you have a kernel. And in Conway scheme of life, the kernel is just 3 by 3 cells. But now we can have a bigger the 10 by 10 size of kernel, and you do a convolution operation with the world, and you have the result, which is like some kind of blurring of the original pattern. And you pass this pattern, this result through some kind of Gaussian function, you get another result, and you have a 1/10 or 1/100 of this value add back to the world, and you also crypt the value back to between 0 and 1, and you get this kind of dynamics, like PDE kind of dynamics.
Before you go on, Bert, so that, the kernel there, thinking about kernel that we normally use in integration, right? Is that kind of a similar analogy?
Yeah. So
Similar to that?
similar to, it's a convolution.
Yeah.
So
that every component of the world is going to be sort of modulated by that kernel.
yeah, it's modulated. If we change the kernel, we change the shape of the kernel, or we change how many rings are there in the kernel, or even different kernels working together. You have different dynamics. We have different patterns in the world.
So in a way, that's quite different from Game of Life, right?
Yeah.
Like there's no equivalent to.
Yeah. Game of Life, you have a fixed rule set. Like if there are 2 cells, then you're alive. If you have 3 cells, you give birth. Things like that.
Sure.
Really fixed.
So there could be an equivalent. You could construct a kernel that would give you this.
So the interesting thing is the Game of Life is only one special case in Lenia.
Right.
You can only have 3 by 3 kernel, and for the growth function you have some kind of step function, and then we have the same. Go back to the Conway Game of Life. So we can say it's just a special case in Lenia. Yeah, it does. I try to make a.
So you can do it. But I guess that the kernel then becomes a crucial modulator of behavior.
Yeah. Of course, the behavior will go back to the discrete kind of CAU. Yeah. So the one of the motivation of Lenia is to generalize the Conway Game of Life or different life like cell automata to become something more general.
Yeah. I guess, it's worth belaboring this a little bit because it's an important choice, right? And so what does it mean if we think about this biologically, just for a second, for the biologists in the room? So you have an agent, or in this case, you're calling it the world, but there's some non-zero values in the world, and they're being transformed by the kernel. Is that a kind of like their interaction field? Their like how could we understand the kernel?
Yeah. So one way to understand what's happening here is each element or each cell in the world.
Yeah.
You can say it's a cell or it's a chemical molecule or things like that. And the kernel is giving a sensory range of these elements.
Yes.
So the range is, you can say is you can make it a Gaussian kernel, or it's a ring. Ring that means it's sensing a little bit further. Or if you have a very complex kind of kernel, that means it's a very complex system of sensing its environment or the other elements. Yeah.
So the fact that there's a hole in the middle of that kernel, what would that mean? That it doesn't sense its immediate neighbors somehow?
Yeah, it's sensing a bit further.
Right.
This ring-like kernel is giving.
Can the kernel be negative?
Yeah, it's possible.
Because you could have a repulsion, right?
Yeah.
So for example, you could, in the hole, instead of being zero, be negative.
Yeah. I haven't tried that, but some other researchers tried that with have a negative kernel. So it gives some other interesting behavior.
So continuing on that, I'm kind of wondering if the kernel itself can potentially change over time, because so one of the things. I mean, in biology, if we look at a cell, so inside the cell you have different genes, some of the genes are expressed, but from the evolutionary point of view, some of them are more prone to error, some of them are more conserved, and they are unlikely to change.
Yeah.
And I'm kind of wondering if some of the elements, or say if your kernel is kind of like multivariate Gaussian, if like one part of that could be potentially more prone to perturbations.
Okay. So the system, depending on how many components, how many kernels, how many co-functions you have, you can have many parameters. Like you change the growth function, the mu or sigma, you have 2 parameters. For the kernel, you have many parameters. So for a complex case, you have up to 100 parameters. So you can see, I will describe some of my recent experiments that actually each pixel in the world, you can have its own set of parameter values. Yeah, it's like you can change over the space or over time as well. So yeah, your question is very good because it's definitely worth going for this direction. So like if you change it through space or through time, what happens?
What are the parameters, at least some examples of the parameters?
The kernel is itself a Gaussian function. So you have mu and sigma. You can change, now you have 2 parameters. You have multiple kernel rings moving around, so you have 2 times something. And the growth function is just 1 Gaussian function, so you have 2. So for each pair of kernel and growth function, you have like 10 parameters, and you can stack many kernels. That means each cell can have different sensory range working together. We have different chemicals, we can have different signaling molecules working together, right? So we can stack this together. You have 10 such kind of kernels and growth function. You have 100 parameters to tune. So it can be learned or can be evolved. So yeah, that's how we can train this model to do something we want.
Sorry to interrupt you once again. I just want to make sure that I understand this.
Sure. Yeah.
The black area here is the lack of available information in that.
Yeah, you can say the values near 0.
Okay.
No activity. Or you can say no cell here, or you can say there's 0 concentration of something, a chemical value, or 0 concentration of cells,
Gotcha.
depending on what you want to simulate.
Thank you.
So I was just wondering with this, so Conway's game of life is purely deterministic. There's no randomness in it. Whereas most of the kind of cellular automata that we work with have some level of stochasticity in them. Does this framework allow for stochasticity? And what would that come in the Gaussian filter or in the kernel?
Yeah. So you can add noise into this system, like just throwing random noise, or the updating itself can be stochastic, like only 50% of the time it will update per pixel.
Yeah.
You can do that. So the interesting thing is these patterns have certain kind of tolerance of this noise. So if throwing in 20% of noise into this pattern, it will survive, like the patterns will still go on. But if like 50% or too much noise, it will just disintegrate.
Okay, so, and that noise, for example, is just you kind of modulating the environments around the pattern in some way.
Yeah. Modulates like to test how robust this kind of pattern. It's usually like this.
Okay. Thank you.
So it's usually we don't give those random noise in this system because the system itself is quite chaotic.
Yeah.
Just like evolve.
Real quick, what is clip on the bottom?
Because if the values is in the world is usually between 0 and 1, is low, like normalized. You can have 0 or 10 or between -1 or 1. Is still this kind of pattern, but usually fix it to between 0 and 1. You can have few values between them.
You mean like the domain? Are you talking
Yeah,
about?
the domain of this.
Okay, well, because you're doing a convolution, so it,
Yeah,
yeah, okay, got it, okay.
Yeah, it's usually if you don't use the create function, you just go to infinite.
Yeah, all right.
But in some other case, like I work with the Nagoya University in Japan, they come up with a system that's very nice. They don't need a create function. Yeah, but it becomes something. The patterns become smoother. But there's some. That's how you play with this system. You can add, you can change, you can remove that stuff, you can stack things. So Lenia is not just one system. It's a family of how to say. It's a family of things that you can play with.
All right.
So the create function is just the original Lenia. These are the original patterns that are found in this system. This guys, this OBM is the first things I find in this system, but I find many other patterns. They are moving, or they are rotating, or even they can bump into each other.
Are these patterns all with the same kernel?
The same kernel. So it's already the simplest kernel, like just a ring-like kernel. We already see these patterns depending on the growth function, that is the Gaussian function, and also it depends on the initial pattern. You can already see this diversity.
I guess I have two related questions. So how did you decide to start looking at the ring kernel to start with? And how did you go about looking for these shapes?
I tried the normal, like Gaussian kernel. The nearest is the highest, right? This is the usual thing, right? But I don't see many interesting things there. That just like some rod-like structure. Yeah, and that's all. No, nothing special. But I try different things like a ring-like kernel, and it's come out with this very diverse kind of structures. So it's stuck in this, and also it's kind of relate to convex scheme of life, because convex scheme of life, you sample the X cells in neighborhood.
Right, but not.
And the center cell is not much in the equation. It is in the equation, but is another part of the equation. So it's more like sampling not itself, but a certain distance from itself. So it kind of makes sense in hindsight.
And how did you go about finding these forms?
Just randomly, random. I'll show you the next slide. So this is a parameter space in the left side. It's mu and sigma. Sometimes I just give it some random numbers and see what happens. And sometimes I will give nearby values and to like a search through the parameter space.
Sorry, mu and sigma referring to what here?
The mu and sigma of the Gaussian function of the growth function.
Oh, okay. So same kernel, different growth functions.
Yeah, true. Yeah, same kernel, different activation of the growth function.
But in the early days, you just did it by visual inspection. You're just looking for interesting patterns, and then more recently, you're finding some. For finding like increasing the parameter values part, I use some Python program to do it for me, like searching through the parameter space. But for which pattern is interesting, I just look at it in my eyes. Oh, this is interesting. I just save it. Or this is, or I see it before. I just
I'm not going further. But I try to categorize them into different species. Yeah.
And how did you initialize the domain? Last question about it. Overall, yeah.
Initial depend just random noise, or stuff from other species. But I put this guy into another values and see what it will change to something else. So in one time, I start with this guy like a rod-like shape. I cut it into half and mirror one part. So I just see what happens. It turns into something like rotating gas. So it's kind of like just play with this. It's like a octopus of some organisms. So yeah, so like an astronomer or like a biologist, I try to categorize them, and also I try to study them more closely. Like, oh, this is the one that rotating, and also some of them have 5-fold symmetry. I try to use some Fourier transform to detect the symmetry. And also for some patterns like this orbium, I call it orbium. They have this kind of interesting dynamics. Yeah, they kind of bump to each other, but they don't die because most of the time they will just vanish or like explode. But for these guys, they kind of retain this kind of particle kind of physics, or even they will form a twin that keep going. So I really like this pattern. So I will do more study on these guys. And these are some, if you have multiple channels, RGB channels, we have stack more kernels. We have 20 kernels for each channel. For channel, I mean, they're parallel worlds. They kind of, you can say different kind of cells or different kind of chemicals exist in the same grid. You can say that. So they have more complex behaviors, or we can find these more complex structures. And we start to see this kind of, these patterns retain their own individual, and also they kind of have some complex multi-agent behavior. So we start to play with these much more complex patterns. So in the early days, like 4 or 5 years ago, I tried to do some quantitative study on them, like mapping out the parameter space, which are the species. And also I measure the speed and mass of these different creatures, and like a project graph. And also some more detailed study, like tricking the parameters, what will be the change in this their behavior? Will they go faster, or will they become something different? And also this come up with the question in biology, what is a species? Like if you have a lion and a tiger, you mix them together, you become a liger. So liger is a new species or what? So even in cells or in virus study, you have so blurry kind of boundary between different species. So we see this kind of things like when I try to categorize them, what is a species? So here, what makes this a species, like a region? Sometimes they are buried, sometimes they are not. So we see the similar questions come up like biology. Yeah, these are some cool simulations done by a researcher. Please.
So what do you mean by by strange attractors?
Strange attractors. Oh, okay. So if you plot the speed and mass, the trajectory of one pattern. Maybe one type of pattern is oscillating. The speed is changing. The mass is all changing. You plot it in the space, in the phase space, called the phase space. They do it in physics. So it will become some curve, like is having some kind of periodic behavior. And if you have this related, you change the parameters, you have a family of patterns, right? And each of these will be have different behaviors. Some of them will like do it this way. Some of them will like alternating. Some of them will just go smoothly. And if you plot in this phase space, we will see this kind of different attractors. I was to say, attractors is just a temperature of movement, so to speak.
It's the y-axis
Uh,
on the right, sorry.
This is mass. X is mass. Y is some other measurements, like the size of the creature or something.
I think another analogy might be something like a fitness landscape, where you're sort of drawn to like a maximum, right? And regardless of where you start, you end up there somehow.
Actually,
And
if a genetic landscape would be even better.
yeah,
True.
agree. True.
So
Sounds
the-
like you got it.
Yeah. So the landscape is you have a attractor. If you like move a bit of the pattern, you remove something. Sometimes you will die, but sometimes you will go back to the original pattern. So it's like a attractor that it will remove it a bit, but you go back to the same route. So we call this some kind of attractor. But if it's chaotic, it's this side of pattern, it becomes chaotic. So it becomes some strange attractor. It doesn't go back to the same route, a similar route. So yeah, that's how I call it strange attractors.
Quick question about the collisions that you showed us before. I'm kind of curious, do you observe any sort of death of agents? And I don't want to use the word agents, but I don't really have any better idea of how to call the structures. But I feel like in real biology, whatever it is,
They do something, right? They do something.
they do something. If they collide, like I could imagine that even if we are not talking about biology but physics, I mean, collision could potentially cause some sort of dissipation of energy or anything like that. And at some point, there is just not much else in cell, and the cell will die, or a particle or whatever. And is there any form of loss or memory in this system?
There's no memory here. No learning, no memory. You can say it's some kind of physical particles just colliding and repelling or attracting. So it's more like physics here. Nothing else. But I will talk about another project I do with Lenia. They do train the patterns to have some kind of agency. They kind of react to the environment and do some reaction. So yeah, I'll talk about it later.
You can see one die on the right too.
Oh,
The left as well.
Yeah, some simplest form of agency there. Maybe you can say that.
See it bounce off there and then.
yeah.
Yeah, but it's more like reactive. Oh, something pass on me. I turn my angle or something like this. More like particles bump into each other, but more with elastic collision. Yeah, so, yeah, they can make even they can glue together. Yeah, I really like that. Really like these patterns. So we, based on this study, so this was my original paper, and some other researchers, they find it interesting. They like EMEA in France, or the Google in Switzerland, or some other university in Japan. they try to contact me and we do some joint projects. But this is still my own project. So I try to use some kind of evolutionary algorithm in finding new patterns. So it's very simple, like mutate the parameters, or we call gene. I'm not sure is a good word to use gene, but yeah, it's mutate the parameters, mutate the structures, and then select for stability, or maybe select for interestingness. That means, oh, I find this interesting, I will save it and further evolve it. And so I find this, at least I find this lineage of patterns. They have different behaviors. I will show it later. So the swarm I show is just some cell-like creatures going around. And the team in India, they try to use some automatic ways. They call it curriculum learning. That means searching not randomly, but they will remember which space, which location in the search space is already searched. So they will search somewhere else to try to search for more kinds of behaviors or different space, different locations in the vector space. And also, I work with the team in Tokyo, Google Tokyo. They have a library called EvoJax. So I just write a few lines of posts, and I tell it to, can you evolve the fastest moving or fastest spinning creature? And the program will just automatically evolve the creature for you. So this is the original creature, and they give the result of the optimal kind of creature.
Is this on the GPU that you simulate?
Yeah. JAX itself is a very good library from Google. Yeah, it's good to use it. It's take care of GPUs and even TPUs to resource multiple GPUs automatically. So it's very good. I just write a few lines using JAX and it will use GPUs. I don't have to take care about the GPU resource, when we use, how it's distributed into different GPUs. It will just do it for me. So I think it's just a demonstration, not much usage to fastest. So the recent projects that maybe you have more interest is I try to have a really, really large work, like 1,000 to 2,000 grids. And also I try to, because of all the experiments before, the parameters are the same for the whole grid, it's global. But here I try to, each pixel has its own parameters or its own gene, so that it can change through time and through space. And I did a lot of change in the system to make it work, so it's not trivial. So here, I start from some self-replicating patterns, and it kind of evolved into some intermediate state and go into some end state.
So what are the selection criteria here? What sort of defines fitness in here?
Okay, so the fitness function is, there's no fitness function here, just to occupy the space. Because to give more details, when a pattern, the pattern you see just now, if it's going through space, the parameters will go with it. Like elsewhere, the black space has no value, so-called genetic information. But if a pattern goes through space, we will have these parameters go with it. So it kind of propagating through space. Yeah. But when two patterns collide, And if they have different parameters, we have to decide what will be next. So in my system, they kind of average out, but slowly average out. If they collide and bump and then depart, then it's okay. They'll retain their own parameters or their own genes. So they kind of compete for space. If one species is self-replicating and is very good in self-replicating, it will occupy more of the space. But if some species is just itself or you die out and you get eliminated.
So they replicate, they can die, and they compete for space.
Yeah, they compete for space. So you can say, space is the fitness function here. Yeah.
But again, none of it's explicit, right? It's important to say.
The good thing is the fitness is it didn't tell it. It just do it inside the simulation. The only thing I do is like mutate. I use some, give some spark here and there, and the parameter will change a little bit. So I only do some mutation here and there for some rate.
So when they collide, you said basically averaging things out. Would it be possible?
Yeah, averaging out, but I try to keep it very slow.
Is it possible to implement recombination and sort of when they divide, split?
Yeah, that's the next thing I want to do, like recombination or keep it just itself. Don't average out. That's what the next thing I want to do, but it's not that simple. I have to think about how to design the system, come up with recombination or things like that. Yeah, they'll be very, very useful if we can do this.
So is the sort of end game consistently like line world?
Yeah, the end game is the line world. So the actual original goal of this study is going for something called open-endedness. Open-endedness means, can we have a system such that it will give out infinite possibility of novelty or infinite amounts of complexity that can maybe keep increasing. The best example is biology, evolution. It gives you infinite amounts of different species. Or human intelligence. You can have like infinite combination of ideas. Maybe it's not infinite, but we don't see the upper limit. So it's something that we want to achieve inside an artificial system. It's not there yet. It's very, very hard to design a system with open-ended things. So even here, after like a few minutes of simulation, it becomes some kind of linear kind of creature, kind of dominates the world. I don't know how to eliminate that, but it kind of become the optimal solution to this world.
But if you like disrupt it and like leave like 10% of the big creature, would you get like to higher level of complexity, where it would be stuck in this sort of local fitness peak with this creature just reproducing itself?
Sorry, can you repeat it?
So like you're saying, like he ended up basically with this kind of thing occupying the whole domain, and basically things kind of stop. But what if you just like remove 90% of the domain? Would this thing just reproduce itself, or would you get additional evolution?
The thing is, you have to detect those large areas, right? And it's not trivial to do that. And it's also some kind of intervention to some manual stuff to do that. I don't want to do that very often. So I do some area search, like if there's some large area, I just remove that. But these linear creatures kind of escape from that punishment. And I cannot think of other ways to punish them. So they kind of stuck to become the end game of this simulation.
So you're thinking about sort of evolution of life on Earth, they have sort of catastrophic events that's like wiped out a lot of things, but
Yeah,
it creates
it's
like new
kind of-
opportunities
Yeah.
to explore.
Yeah, so maybe dinosaurs at that time is already the optimal of those maybe warmer kind of environments. It's kind of stuck maybe, but a asteroid come into that wipe or then mammal becomes the next optimal solution.
Yeah, but it might be sort of, there's one possibility is that it's kind of the optimal solution for the given environment, but maybe it's kind of a local fitness peak that's very difficult to get away from. And if you sort of create a new opportunity, you might have an
Yeah,
emergency.
sure. So maybe biology is not as open-ended as we thought. Maybe it's still the species are kind of optimal in their own niche or own environments, or at least for the time being. If you wipe out all of them, the dinosaurs, or in the Cambrian explosion, you wipe out some of them, they will some other new creatures will come up, but they have a better adaptation to everything in the environment.
If I understood you correctly, then a mutation here is not necessarily affecting fitness or whatever people would like to define it normally fitness as, but as more of a capability of explore the space around.
Yeah. So this is just this case. This case, the fitness is just have occupied as many space as possible because of the design of the system.
Yes, and the mutation is affecting that capability.
Yeah. You mean, I mean, this, I'll show the movies.
Okay, awesome. I love this.
So yeah, start from these self-replicating guys. We have different, the below is penalty off. So I don't penalize those area creatures, but they do have high mutation rates in both cases. So in the top, you can see those area like things got wiped out, intentionally.
Yep.
And the below is just they just occupy the space. And the right side you see the different genetic or the different parameter values as different colors.
Oh.
So the end game is in the top.
Oh, Caesar time. Yeah. Absolutely.
So the end game of
So your work is interesting. Yes, absolutely. That's beautiful.
the end game of the phase above is linear structure, because we kind of success in eliminating those area patterns, but the bottom is those area fast growing, going glue-like things win over all other things.
How do you impose that penalty?
I try to measure, I use some kind of diffusion thing, backward diffusion to get the area. And then if the pattern is occupying some area, then I will use this measurement of area to remove some or mutate the area of pattern. Something like that.
Yeah, I mean, we discussed a little bit before this, but for the sake of the group here, often evolution occurs under a certain selection pressure. And so the pressure here, I guess, is some sort of spatial constraint, but like death or life or death is normally the selection pressure. And that's normally driven by lack of resources or predation, some sort of predation. Is there a way to kill things here, like to?
Yeah, you can say that
sort of
occupied
touches on
space is also killing others. So,
yeah, so the idea of predation being something that you had evolved under predation versus not, would you get different organisms, right?
Yeah, you can say that's maybe you can say that it's predation, but it's more like occupying the most space is the best. Is the emergence phenomenon here in this system.
If you drop one of these line creatures into like an earlier stage of the world, will you see it kind of like predate the creatures and create more of itself and take over pretty quickly?
Sorry.
Like if you, like, you know, going back to an earlier stage, right, you kind of have these like, with almost like a cellular tissue pattern type of thing.
Yeah.
If you drop one of those line creatures into that environment, right, just like remove whatever was there before, like in like a little square or something,
Yeah.
and then substitute in, you know, one of these isolated line creatures.
Yeah. They may survive, or they may survive because they may not wipe out all of this already. They may be disrupted by these guys. But if you, because it's like in the end game, they already take much time to propagate and replace all other things already. So yeah, you can say it's kind of cancer. You can say you can treat it as another cancer. So yeah, they take the time to evolve and also to eliminate all the diversity in this world. Yeah.
I guess what I'm asking is like, because this line creature is suited to, you know, the evolutionary trajectory that it came from, but that doesn't necessarily mean that it's competitive with creatures in the earlier stages that it never had to compete with because it never actually met them.
Yeah. True. That's why if you ask me put the linear thing into here, they may not be able to eliminate these guys. Maybe the line go there and get disrupted and will die. Yeah, maybe because these guys are very good in self-replicating.
But have you tried it?
No, I tried it.
Cool.
I'll tell you the results.
Right.
Yeah. So I'll tell you a bit later, but I try to implement food. I have a food channel or energy channel in this world, which is kind of like an environment, and also have a specific mechanism that this pattern will consume energy in that channel, and if the channel get lower value, it also like affects these channels to have lower activity or even lower growth or lower activity. And by doing so, it seems like it's very good in confining those structures into like cellular structures, like keep them into circular shapes. And we don't even need those penalties, like those linear structures or area structures. They will evolve, but they will finally occupy, but much later. It seems like giving a food constraint make the creatures more self-contained, but not like avoiding them to expand indefinitely. So there's some very unexpected thing, or expected, I'm not sure, but some very interesting experiments that we can do. Yeah, it's in the middle of the experiment. I have a dropper tool. I just click everywhere and see which kind of cell is, which kind of species is actually in that space. So each point is actually different species. You can see. If you put into a petri dish, then you can see the actual behavior of that species. But there are some kind of coexist in the larger simulation. Yeah, there are some other experiments like trying to find the objects automatically using some method, or also some other earlier using WebGL that you can see in your website. You can actually play with this on the website.
Are there any interactions between these creatures except for competing for space that might, the interaction that might influence fitness, where it might sort of be beneficial for one species to be next to another, and then it becomes difficult to disrupt this?
Sorry?
So like in your case, you can have a heterogeneous
Yeah.
species.
Yeah.
Question is it kind of completely neutral and by chance, or is there any positive interaction between species in some of your patterns?
In those.
Yeah. So do they interact? Are there any other ways for them in here to interact? Maybe some emergent interactions apart from the spatial
Okay.
competition.
Yeah, as I said before, there can be other design of the system, like how to recombine in generative, how do we combine, or in this cell level. Yeah, it's also kind of diffusion. What I'm using now is diffusion. They will kind of average out the values, but I think it's not that.
I'm not speaking about fusion, about like kind of the green center in the center. They're not getting out competed by the more numerous species. Why is this? Do they have any advantage of being in this local environment due to interaction with the others, or this is entirely stochastic?
So just now you can see that actually many of the species, if you put it in a petri dish, they're actually expanding. They're actually competing space already. So, for example, if actually these green guys are already losing the space. If you use a dropper to put them into somewhere else to see how they behave, they are actually not much replication going on. They just stay here, or even they are actually disappearing. So there's kind of the regions they are shrinking, but others like here, you can say here or here, those winning patterns they are expanding a lot, like squeezing space from other species.
What is all this on the right?
Oh, it's just this is the parameters, like
Okay.
using colors to see the other parameters mutating. These are just the kernel or growth functions. Yeah. This is the kernel.
So there's a lot of parameters going on, and like
Yeah. There's like 1, 2, 3, 4. It's more than that. I just crammed down into a few parameters. There's a lot of parameters going on. They can be tuned or evolved in this case. So maybe this experiment is more interesting to you.
I guess one more question. So depending on what parameters you put in, do you see like could you, for example, have the parameters be such that on one half you kind of like cut the world in half, right? On one half you get like one dominant species, another half another dominant species, but they can't really interfere with each other too much because the parameters are too distinct that create these niches, right?
In this case, because I'm averaging them, if the two species are very different, like coming from different space of the grid or even different time, they kind of, I hope they will like bump into each other and repel something that will be better. But if they stick together, they will just average out the value.
But I mean, like depending on how you set up the world, can you see like stable states where there's like species A on one half and species B on another half? That'll be like the most basic version of this like sort of niche idea.
I will show you another experiment later.
Okay.
So I will talk about another topic. Is using machine learning to find some patterns. So here, the patterns it is from the team from image. Like we have one channel, but like 20 kernels. That means the behavior of these patterns can actually kind of diverse kind of behavior. And at first, if you put a pattern, and then you train for survival. That means the patterns have to go through the space. That's the first thing. And then you train you change the parameters so that the patterns can go further and further in space. That's the second thing. And then you try to add these obstacles, the blue obstacles, into the world. And then the usual case is if a pattern bump into this wall, it just disappear. It's what we want, but as we keep training the patterns, or we keep adjusting the parameters such that now and the result of the training is the patterns learn how to survive from this collision.
What does wall mean here?
Just keep removing mass from this blue space. That means it's like more like a black hole.
Yeah.
But usually, if you bump into this kind of hole, it will just disintegrate. But now they learn, because we have many kernels. Maybe they are working together to sense the environment and to act accordingly. Like you can see, some of these patterns will turn a bit to avoid those holes or obstacles, and they work together to have some kind of reaction that makes it survive in this environment.
I have a question. So these walls, do I understand correctly then that they have to be like at least the width of the kernel, so that because then that way you're not like going through walls.
Yeah. So they're actually a channel. The blue is actually another channel.
Okay.
Which our design is the channel will have a very negative kernel acting on the yellow channel.
Okay.
So that if you bump into the yellow pattern go into the blue channel, it just remove all the stuff in the yellow channel.
Okay.
So you can say it's some kind of wall, or it just have a negative influence on patterns.
Was it trained, the agent, on that sort of hand-drawn tunnel there?
Yeah, we just control these things. I try a circular spiral, and it's go through this spiral.
So once it's trained on one, it can do many.
Yeah, that's the two things. We only train on dots, one kind of dots. So it turns out that it also, after training, we call it the generalization. We generalize to other unseen tasks, like bigger dots, different walls, even different shapes of walls. They all do well. Even we don't train it for this kind of shape of walls. We only train it for like a survive from those dots, the small dots. That's all. We even move the dots, they still survive. Like we only train for static dots, but if you move the dots, they still do okay to survive from the blueness kind of dots.
When you look at the kernels, is it can you understand what it's doing, or is it too complicated?
Maybe next time we should like really analyze what's inside the kernels. Like we move some type of kernel and see why they have such kind of ability from the training. Yeah.
I mean, an obvious thing for me is this learning to conserve mass.
They don't conserve mass.
No, they don't have it. It's almost like it's learning to do that.
Oh, okay.
In the sense of that, if it fragments, it dies, right?
Yeah.
And so
somehow. True. One thing they learn is to conserve mass, whatever the situation.
Yeah, because then they're sort of indestructible in this world.
Yeah, they kind of learn survive it. So the good thing is the next one I show is here we add a food channel, which is the food channel is the green channel that I talked about. If there's no food, they'll just die. And also these red guys, they are not trained to deal with this situation. They just trained with obstacles. Like they kind of they try to find those areas with green area, which is not trained at all. But eventually they die out. But this bonus they generalize to unseen tasks that's not trained. but because of how they get the channel to survive anything. So in this scenario, they still, because they have to survive somehow, so they react to the environment in some way. That's good.
So because I was just wondering for the food, obviously when you talked about avoiding walls, you kind of said the wall was like really negative value, that then kind of cancels out in the kernel.
Yeah.
Is the food then a positive value, and it's kind of like an inverse
yeah,
wall?
the food is the interaction is the red channel pass through the food, they will like lower the value of the food, and also if we have low level of food, if you have a negative effect on the pattern.
Okay, so it's like an inverse wall.
Yeah. And also the food channel may be slowly regenerating
Okay.
through time.
And then another thing I was wondering is, what's its knowledge of the environment like? So, for example, on the maize problem, can it kind of see? Is there a limit to the kernel? That, what it can interact with the environment? Can it effectively it can kind of see through walls? To see
No, it's still the local environment. So.
But that's not limited. The extent to which it can see the local environment isn't limited by the environment itself, only by the size of the kernel.
So it's kind of not there yet. Like it doesn't have memory, it doesn't have learning ability, it doesn't have this kind of chemical to chase through the maze, like slime modes. So, but we can imagine that if we implement this kind of food in the maze, and it will be able to detect which place it has visited. So it will solve the maze much more efficient. We can imagine this kind of how to design the system to make it better.
I have a question. When you're evolving, what is it exactly, like what feature exactly is being varied here that you're selecting for?
So
is it like the growth function?
Growth function and the kernels.
And then also the kernel.
Yeah, the kernel, because the kernel are just one or two Gaussian functions.
Okay.
Yeah. So with different Gaussian function parameters, like the range will be further or narrower. That means changing the sensory range.
Right, and this is like, and then when you finish the selection, it's constant over the whole domain now.
Yeah.
Right. Okay.
With there's still some limits. They won't let go.
Right. You have
too far.
Right.
Some limits of how far the kernel can go.
Yeah, but I mean, like this domain that you have, like the parameters are constant across the whole domain.
Yeah.
And so it's a deterministic system now, like fully deterministic, right?
Yeah, it's global.
Yeah.
It's not like.
It seems like you could have a sort of perception by like if you made a very big kernel and basically like kind of generate food or something that the agent can pick up on based on if that kernel detects something that's your target nearby, right? Then the agent can use that as an intermediary to kind of itself know where to go.
Yeah.
I mean, it's maybe kind of obvious, I guess, if you but.
But then wouldn't a very large kernel also imply a lot of variance? So the future actions of the agent would be kind of much more stochastic.
Not stochastic, but I mean different size of kernel can add as different sensor.
Yeah.
Like and also different range of reaction as well. So if you have small kernel, like 20 kernels, one of them is small, then it's like detecting smaller region. Then if I have a finer reaction, and for the larger range, maybe the sensor further than if a larger movement. This kind of work together.
Yeah, and in that case, you can also have like one large kernel and some smaller parts.
Yeah, we do.
Cool.
Yeah, in this study, we do like look at the kernels. It's a sum of the bigger, some of the smaller, if we remove some of the smaller one, it's okay, it's still okay, but some of them are important. Remove them, they're not working. And the bigger ones also the bigger, it's not working.
I'm wondering about like if your kernel can be directional. I'm imagining like
Yes,
like
yes.
having a vision, but then you also need to be able to like each pixel needs to be able to have some orientation. Like okay, I'm
Yeah.
looking up, looking left.
Yeah, they'll be much harder to
Yeah,
design system.
yeah.
Yeah.
Plus, it's like the whole you're dealing with like
Yeah. If you have directional kernel, but it's global, then everything will be going.
Yeah.
You have a directional.
Yeah. But then in that case, like each pixel can have its own
Yeah,
orientation, so that it's
That's doable. That's doable.
that's interesting.
Yeah, we can design a system to have this kind of bias.
I guess, say what I'm sort of thinking about it more, like, say that you have like your cell, the yellow here would be like let's call that current or world A, right? And then let's say you have a target, that would be like world B.
Yeah.
And then you have some like third world, which I'm gonna call like the detection world, and that would be world C, right? And you have a large kernel for world C, that it basically multiplies you need A and B to be detected in order for C to go up. Right? That would create a local growth of C within creature A if it's close to target C.
Okay. Yeah, that makes sense. Like even you can have some kind of diffusion inside channel C. So it's like giving more information to the creature to go to get the target.
Yeah, it would almost be like you're basically coloring the creature based on its proximity to the target almost. Right?
Okay, yeah. That's also possible. Yeah. Yes.
But it could then, it could use that information theoretically, right? That could be incorporated into how it responds to, like it could respond to C in some way.
Yeah. That's very good suggestion. That because this is one channel, right? We have like play with three channels RGB, but you can also add many channels, which is hidden. You don't even need to know what they are doing, but the evolution or machine learning will figure out, this channel can be used for memory, this can be used for some kind of signaling, things like that. Yeah, it's possible. So talk a bit about how to train it. This is something called neural cell automata developed by the Google team in Lake. So it's one kind of machine learning or deep learning. They are just if you know about machine learning, they have L2 loss, feedback to the have a gradient descent, a backpropagation through time. That is how they do train the neural network, the cell automata. What's showing here is they trained the cell automata to a gecko emoji. But the good thing is, if you disrupt the pattern, it will regenerate the pattern. So that's what their work is doing. So we kind of use this NCA as an inner loop of the training of the training used here as an inner loop. And the outer loop, we use comes out curriculum learning. That is, we have a target, we have a pattern. If we give a curriculum to it, like we should go the targets further and further targets, and the pattern will be doing better and better than to go through a space. And then after this curriculum, you graduate, and then we have a next part of curriculum, that is, we start to put obstacles there so that it start to learn how to survive from the obstacles. So you can kind of like multiple stage of learning. So it's the outer loop. Like in each step is learning from NCA of the task. And the third thing is how to design the environment. Like, should we add obstacles? Also, we add energy, or as I said, should we add some kind of intermediate chemicals for it to use, something like that. So with different environment design, we can train different kind of. So we can keep designing Lenia by putting different kind of system design. One thing I said before is adding energy constraints, like having a layer that is acting as some kind of energy that may have some good effect on the patterns. Another thing with also working with NVIDIA is how to say, the system I just said is just adding or subtracting value from the kernel, the result from the kernel and the growth function. It's just adding up and down. There's no restriction of the total amount of mass in the grid. So the pattern just can vanish or just explode. But here they come up with a gradients kind of updating. So after calculating the convolution and also the growth function, we have result. We use this result as some kind of gradient. So the values are moving along this gradient. So with this kind of gradient law, they come up with this result. So you can see you don't have to even keep track of those the total mass. The total mass will be keep constant throughout the same simulation. It's good that you can do evolution or training much easier. So they kind of train the patterns with can you have the optimized for angular movement. So this pattern have the optimal angular movement. We don't have to even have to train for survival, because survival is built in the system. Some other experiments, like have some food packets, or in the right side, you can see this kind of species having some niche of their own environment, own space.
How did they decide what to color those?
Each color is one species.
Okay.
So
I mean, they must use some kind of way, like how do you identify a species, right? It's all just.
they just colored by different combination of the parameter values. Yeah. So just the one.
Okay.
Yeah, one combination is one species.
So they have like they're different worlds, but the worlds can't intersect, or they're sort of repelled from each other by sort of maximum density allowance.
Yeah. So I'm thinking in this case the mass is not perfectly conserved, because if it's perfectly conserved, it just have the small amount, but it can grow somehow in this scenario. Yeah. So for some species, they will try to dominate the space, but not too much.
How did you select each of these species then? Were they like independently selected for mass conservation, or what?
Mass conservation is built in. It doesn't need to. It just they are just occupying. How to say?
Oh, you don't need to train for that.
No, we don't have to train for survival.
Okay.
I guess it's like if you're kind of surrounding volume like of a different type, then you'll start to convert it into your type faster.
Yeah, it looks like this kind of thing. And also you can see multiple colors in the same region, like pink and white. They're actually two species. So they kind of have some kind of symbiosis already.
So I think I missed something. How do you define species in this context? Is that just an agent that's been trained separately, or are these based on the singular agent and the species is just how it's configured?
Yeah, and similar values in the parameters. And
Okay.
they have similar behavior. And they kind of group together, or they have similar behavior.
Okay, so have they been trained separately, these species, or is this based on one trained network?
They also have a pixel level parameter values. So they kind of, that means just a pattern that have similar or the same parameter values, they happen to occupy the same space in here. They will say it's just the same species.
Okay, yeah. And those parameter values are immutable throughout the simulation, they can't change. The parameter values immutable throughout the simulation.
In this case, it's not immutable, but of course we can mutate the cells.
Okay.
In this case, we just put many different initial random species together and see how they
Yeah, sure, that makes sense.
mix together.
But you could do this with Lenia. It's like there's nothing about the PDE part that's necessary for this to happen, right? Like you could do the same thing by having different world layers that you impose some mutual exclusivity to in your
Yeah,
kernel design.
entire different worlds interact together. Yeah. So these are some other variants you can play with, like with the creep is just creep the amount to 0. But if you have a kind of soft creep, that you have this kind of softer patterns that I find their behavior even more interesting. Like they are eating food dots. These are like a smooth diagrams. They kind of like spitting out smaller patterns. So that's how you play with the system. You have different kind of design, then you have other kinds of behavior.
Is there a reason why these are more pixelated?
I just for these two videos, I just make a very low resolution to say that it's still cell automata. We can have a very fine grained.
So that wouldn't make any impact on the behavior.
No. It's the same behavior, the same structures. Just want to let other people know it's still cell automata. Continuous kind of.
On that note, you can see that some of the pixels have different intensities. Is that just because you've converted from a continuous kind of representation to a discrete one, and so instead of each pixel either being kind of on or off, there's now a gradient.
The state is still continuous. You still have a real value.
Yeah,
in the cell. For discrete, I mean the spatial, the spatial pattern. Each square here is a cell.
Yeah. And
that means my neighborhood is quite small, like only 5 by 5 something.
Yeah.
So to demonstrate that these patterns can survive in a very coarse kind of space. It still happens.
Yeah.
What is the clipping? I kind of missed that.
The usual clipping is if you have a value which is larger than 1, then you just chop it back to 1. If you are smaller than 0, then chop it back to 0. This is the usual hard clip. And soft clip is more like if you are above 1, then you go back to 1. Okay. But if you are 0.9, then you go to 0.8.
So it's trying to regress towards 0.5?
Yeah. Like this line in the bottom right. The red one is the hard clip. So everyone just chop between 0 and 1. but the yellow or the green one are more like slowly compress the values back to the 0 and 1. So you see this kind of behavior. It seems like they kind of sensing further away and also acting. I don't know how to explain this here, but they do have some different thing happening here. And also, we can have some, the grid not necessary to be regular. You can have random mesh of points, or you have a sphere, the non-Euclidean kind of space. You still have these patterns.
Much better
What is
savers.
what is Houdini?
Houdini is a kind of 3D software. I don't know how to use, but
Oh yeah.
the guy from Princeton, IS, he used Houdini to implement Lenia. So the cool thing is you don't have much programming to have this kind of non-standard geometry. It's cool. Yes, very cool.
Does it fall off the edge there?
Yeah, sorry.
Does it fall
No,
off?
no. It's a sphere.
No, the one on the left.
Oh yeah, because there's no repeating boundary, so it's just die. In the
So it falls off the edge.
Yeah, I guess it falls off the edge. So this one is the latest one.
Is that like a flat Earth?
So this one is very special because the team in Google Zurich, they implemented on a particle system. It's no longer cell atom, nothing cell automata here. So you have this dot, which is a particle. And they have an attraction, which the attraction is K. The K term is GK term is the same as Lenia. And they add a diffusion term or repulsion term. This is D. If there's no term, there's something like all the particles will like come into a black hole. We don't want that. So we have some kind of repulsion. And we have a gradient consists of this linear field and also the repulsion field. And the particles like travel in this gradient. So they kind of have similar, arrive to have similar patterns as linear. Also 2D and 3D. In the 3D world is very interesting because it's kind of the pattern recruits all other particles, become something else, and also you can see them some kind of development inside the pattern. And once it's finished, they go away. Bye-bye, escape. Yeah.
So David had a question for you there saying, you get so many amazing visualizations. Which one do you decide to choose for which project?
Different kind of visualization.
Visualization libraries or something.
Okay. So my default one is to just display the array as a, just to display that.
What do you use for that?
So if there are 3 channels that I just showed, the RGB channels,
Right.
like the value is just how, because it's between 0 and 1, or you just change it into an image, and then I show the image. It's the easiest way. And for this other visualization is they have some 3D libraries, or they have some other, like Houdini, using Houdini is totally good in visualizing things.
Yeah.
3D stuff. So
This is like a different type of 3D visualization.
yeah, this team is they the WebGL.
Or the purple.
Yeah, WebGL or GLSL. Yeah, kind of like graphics libraries on web graphics library.
For all of the different visualizations, did you do all of the visualizations or, well, not the Houdini, but like, I'm just wondering, like, on David's point, like, there's so many different, is it just, I was imagining, like, different researchers are doing different visualizations.
Yeah,
Is that what it is?
yeah.
That
Usually it's just like this team is.
people have different
Yeah.
preferences?
I mean, it's usually just show the array as an image.
Yeah.
Because the values between 0 and 1 that just times 255 and you get a already image that you can already display on the screen. So here, like this one, you just have different palettes. Like I don't want to just have a boring black and white. So we kind of give a pattern, palettes to here, like go from black to yellow, to black to blue to red to yellow.
Right.
So you can kind of see the different gradients in this pattern, and also make it like cooler inside.
We're running over time a little
Yes.
bit. I'm not sure how many more slides you
That's
have.
the last one. Yeah.
Okay, sounds good.
This is the last
Okay, so I believe there was a question or two. Let me check.
There was one.
I think Coyote has a question.
Yeah, so in an earlier slide, you mentioned that Lenia has fractional updates. Do you mean that your differential equation would be fractional in time?
For fractional, I mean, if it's not fractional, then I just add the or replace the value with some kind of after convolution, after the goal function, I have a value. If I just replace the value with this new value, then there will be something the dynamics will be not smooth, like just very discrete. But if I just add a portion, then the dynamics will become smooth already. So the smoothness comes from like the fractional update. That's why it becomes it can be described as some kind of form of opinion that comes from the fractional update.
Hopefully that answers your question. Any other questions? I know we'll be constantly asking this many questions throughout. So.
Yeah.
I got time later.
Yeah, I think we should let meet now.
Yeah, so just a few notes, like Raphael has already implemented Lenia into HAL. So if any of you are curious to play with this, we have it in HAL now. So thanks to him. And then secondly, just wanted to introduce Showery, who's working with me, a USF capstone student. So you can meet him afterwards as well. Thank you again, Bert. That was fantastic.
I really hope that because this is some kind of very abstract